Hello all, I'm very glad to be here with you today. Dang random a maximum of 14 minutes to talk about security for safety. And as we all know, this is a fairly simple, undisputed topic, so a couple of minutes should be enough. So, joking aside, let's not waste any time. I'll give you a security for safety crash course and also a sneak peek into the future of security and safety risk assessments. So where's our problem with security for safety? May I introduce you to a term that's very helpful in understanding the nature of security and safety problems: emergence. Emergence is the magic that happens when a system comes together. Or more formally, if we define a system as a set of entities and their relationships, emergence is what happens on top. So emergence is the functionality that emerges out of the combination of all system parts, and that is more than the sum of the parts. Now, emergence obviously is a great thing, but it also has downsides. Obviously, no one guarantees you that a system's emergence is always desirable. So let's take an example. A plant produces a product, so that's great. But a plant could also produce, for example, a gas that is harmful to the environment, not so great. And then there can also be unanticipated emergencies. So the plant might produce a byproduct that actually is valuable to another industry. Great surprise there. But maybe that very byproduct combined with the harmful gas causes explosions, killing people, which would be a not so great surprise or unanticipated and undesirable. So there we have it, the common objective of security and safety. We analyze undesirable emergencies and we are trying to prevent them. Or if we want to make it sound a little bit more optimistic, security and safety have the common objective of making systems more resilient, which means making them able to cope with undesirable changes, no matter if they're anticipated or if they're unanticipated. Let that sink in for a moment. There's even a term for that that's called resilience engineering. And while we don't really have the time to go into the details of that young discipline of resilience engineering, you can think of it as a kind of umbrella discipline above security and safety engineering. And here's a crash course on why that is so increasingly important. For a long time, it was enough to be a safety engineer to deal with undesirable emergencies. But the problem is system complexity has increased. And with system complexity, the spectrum of undesirable emergence has increased as well. So safety has become better and better at dealing with the anticipated emergencies, mostly the anticipated ones, and most of it was learning out of errors. So first, safety anticipated mainly technology failures like metal fatigue, for example. And then we started to learn that it also needs to anticipate human errors, like if there are too many alarms, distracting an operator from the one important alarm and he makes an error. He makes a mistake. And the next era was anticipating social technical failures. So for example, a culture of concealment, which could lead to accidents, and that's why safety invented such a thing as safety culture. And for all these events, safety is an answer. The events get included in the system's design base and safety engineers design a system response for them. But the problem is that when the system becomes increasingly complex and it becomes impossible to include all these undesired events in the system's design base, then, for example, one reason for that is that a system offers an increasing playground for human creativity and, of course, with that also human maliciousness. And for these cases, safety methods may fall short or may need to be complemented with something more. And for malicious creative events, we have methods that are better suited for analyzing such like events, which are security methods. And by looking at the systems from a different perspective, from a security perspective, than safety does so far. So while it's a good start, and it's by no means a matter of course, to agree that safety and security have a common objective, that is resilience, that of course is not practical enough to work with. So in a crash course form, what you roughly need to practically work with that is pictured here in these 3 steps. So there are 2 steps that security and safety can actually share. First, defining a shared objective, and second, transforming that objective into a shared scope. And then comes the third, analyzing the scope's risk, and this is where you need 2 different perspectives, one for safety, one for security, so one for non-malicious failures and one for all the creative manipulations. And both perspectives have suitor methodologies for their purposes. So the 2 perspectives, safety and security, have a shared objective and scope, but not necessarily shared methodologies. And while this may sound quite simple, security and safety experts alike have been working hard on that in multiple projects and joint working groups during the last decade. I'd like to share a little of that knowledge a little bit more deeply. So let's look into defining the objective first. Beyond resilience, what can common objectives for safety and security be? Resilience against what exactly do we need? Or in more practical terms, what would be an intolerable risk for us? In our analysis, do we protect primarily humans, for example, or the environment, assets, information, business? You could say all of them, and that may be true, but there are, of course, reasonable scenarios where some of these risks are not a priority. But the most important point here is this objective, however you define it, can and should be the same for security and safety risk assessments. Both security and safety risk assessments have a shared objective. Next, this objective needs to be translated into a scope to have something more tangible to work with during risk assessments. And there is a way to look at scope that security and safety actually can share. And the keyword is functions, because functions specify what needs to be achieved, but not yet how it is achieved. So for example, by which technical systems exactly. And for an industrial control system, you will have basic control functions and complementary functions that support the basic control functions, and you will have safety functions. And the scope, so the functions that are in scope, you could name, for example, essential functions. Let's do that for the moment. Essential functions then are all the functions for which interference can lead to the intolerable risk, the objective that we have defined before. So if our only risk criteria on the slide before has been humans, you would only need to decide which functions you could mess with in order to cause harm to humans. And that then would be your essential functions, so your scope. So the important point to take away here is safety functions are mostly completely in scope, depending on objective, but it's not necessarily only safety functions. So depending on your objective, a large part of your basic control and complementary functions could also be the scope. And again, this is a shared scope. So the functions that are in scope both for safety and for security risk assessments. Up to now, everything was shared. Now for the differences. So if you analyze your scope's risk, you're asking for the causes. So for your essential functions, these are your scope, you're wondering what can actually cause interference with these functions. And depending on cause, you may need different methodologies in your toolbox, as we said before. For non-malicious technical failures and human error, safety has a fairly complete toolset. And for the creative, malicious ways of interfering with the system, you need security risk assessment methodologies. You just need a different perspective, in a way. So the security and safety methodologies are both legitimate, but different. And they may well be carried out by completely separate teams, separate people. But what you can actually do is coupling them. So coupling means finding the most efficient path to navigate through the jungle of 2 separate methodologies. So in an example, we look at coupling the yellow safety risk assessment process from IEC 61511 and the blue security risk assessment process from ISA IEC 62443-3-2. And there are also shared process steps. Those are green, and we've discussed them before. Definition of shared objective and shared scope, for example. Now, what's the most efficient path through the jungle is mainly defined by inputs and outputs. And here's why. In order to avoid unnecessary iterations, you would obviously want to have produced all potentially useful inputs for a certain process step before beginning it. And that really is the entire magic to it. So for example, it makes sense to do the safety risk assessment and allocation of protection layers before beginning to do anything regarding security, because the major hazards and the definition of safety systems and their placement in a network potentially are relevant inputs for the cybersecurity risk assessment, because safety instrumented systems could be attack targets. We've seen that in Triton, for example. And as another example, take for example the zone and conduit diagrams, which are produced on the security side in 62443 after the initial cybersecurity risk assessment. They are not currently required anywhere in safety as an input for the requirement specification or anything, but they could well serve as a useful basis, for example, for defining safety system segregation requirements. So the important point to make is here, methodologies for safety and security can and need to stay separate, but they can be coupled for efficiency purposes. And sometimes, because of this coupling, the coupled process even becomes better than the sum of both separate non-coupled processes, talking of emergence. And the coupling work you're seeing here is actually a sneak peek into ongoing ISA 84 standardization work, and that leads us to our last message for today. Because if you're interested in all this, there are actually two projects to watch. I'm not going into too much detail here, but in a way you can see the 3 steps we've been talking about today as an increase in detail, in the level of detail. So you've got the high level shared objective, you break it down into a shared scope, that's already more detail, and then at the event where you split in a 2 different perspectives, you more deeply analyze scope from different perspectives. And the 2 projects I've kind of introduced you today without you knowing it, look at exactly this in different levels of detail. So the IEC TR 63069 is under revision starting in these weeks, and that is more the high level part. That's really encompasses all the things that you've learned about shared objective and shared scope. And in the future edition is also planning to give examples for the coupled process, but only the process steps. And then ISA 84, technical report 8409, has been under revision since 2019, and that is more focused on the lower level coupled process and also the methodologies. So it aims to define the completely coupled safety security lifecycle, not only for risk assessment, but also, for example, design, maintenance, decommissioning. And in addition to these coupled processes, it also aims at including example methodologies, how to actually carry out each process step. So as my final message today, I would like to leave this statement here. It's not from me, but from one of my ISA 84 WG9 colleagues, who said it in one of our discussions on safety and security risk assessment. And it's both safety and security need to spread their wings and learn what the other is doing. Thanks for beginning to spread your wings today. Here's how to reach me, and I really hope you get to enjoy the rest of the conference. Thank you.